So far we've talked about resistance and capacitance, and now that we've seen Faraday's law, we can introduce the last circuit element, which is an inductor. And the idea associated with it is inductance. In this picture here on the screen, you can see we have two coils, 1 and 2, that are shaped like donuts, and we basically cut them open. And what we see is if there's a current in coil 1, we know we'll get a magnetic field, but the production of that field runs into coil 2. So all of a sudden, when we turn on the current in coil 1, we get a magnetic field going through coil 2, and then we'll end up establishing a current in coil 2. This interaction between the two is called mutual inductance because a current in one induces a current in the other. This depends on a lot of complicated factors, mainly the geometry of the two coils, their sizes, their orientations to each other, their distances from each other. It's really kind of a mess. But one thing we can use is the fact that the inductance in coil 2 due to coil 1, which we might call M21, is the same as the inductance of coil 1 with respect to the current in coil 2, M12, and those two have got to be the same. So it's a symmetry property. So we can drop the subscripts and just say the mutual inductance of the two looks like this. N2 times phi21 over I1, which is the same thing as N1 phi12 over I2. The units of inductance here are henries, and again, this is a capital H because it's a name. And a 1 Henry inductor is a pretty large inductance. The EMF developed in one coil, because the current changes in the other, we would write like this. The EMF developed in coil 1 depends on this M factor. There's a negative sign, Lenz's law. And it's change in the current in coil 2 with time. Things like transformers, which we'll look at shortly, they rely on mutual inductance between two coils. So any kind of non-contact charging, like for your phone or an electric toothbrush, something like that, that's using this same idea of mutual inductance. Now, we talked about transformers being the thing that's sort of built the modern power grid, where we have big and more efficient power plants far away from people without wasting all that power trying to get it to people. And we're able to deliver the power to your house at a relatively low voltage to make it a little bit more safe. So the math involving the connection between the input or primary coil on a transformer and the output or secondary coil is not too bad. We go back to the connection between EMF and changing flux in a coil, and we can write it like this. The EMF, or voltage in the primary, depends on how many turns there are in the primary coil and the rate of change in the flux. In general, this really means the rate of change of the current, because that's what's going to produce a magnetic field, which produces the flux. We could wrap a second coil around that first coil, so both coils have the same value of change in flux with time, and we could use a different number of turns in the secondary coil. So we would write EMF in the secondary is NS, number of coils in the secondary, times this same changing flux. If that's true, though, since they both have the same value of delta phi delta t, we can use this and say, well, if they both have the same value of this, we can say there must be this relatively simple relationship between the EMF in a coil and the number of turns. Now, if we actually want to build one of these, it would be very complicated to try and wind one directly over the top of the other, but it turns out that a piece of iron can conduct a magnetic field kind of like a pipe conducts water. So we can wrap the primary, here we're showing 3 turns, around one side of this iron square, and the secondary about 6 turns around the other side, and they'll both see the same flux go through them, and they'll see the same delta flux delta T. What this means is, let's say we have a primary coil where we have 100 turns and we connect it to the wall outlet. We know that that's 120 volts RMS. Now on the secondary side, let's say we have fewer turns, like 10. What will the voltage be on the secondary side? Since we have this formula, we can solve this for voltage on the secondary side, and it's just primary voltage times the turns ratio, secondary over primary. That's 10 over 100. So that means if we set this kind of transformer up, we'll get 12 volts on the outside. on the secondary side from the 120 from the wall. For this reason, it's called a step-down transformer because the voltage goes down from something higher to something lower. This is actually what's powering your doorbell. They all have doorbell transformers that are about the size of your fist, and they bring 120 volts down to 12 volts, or in some cases 18, depending on the doorbell. We could go in the other direction and say we still plug our primary into the wall, but now we have more turns on the secondary side than the primary side. If it's 500 on the secondary, 10 on the primary, we can see we're going to get 50 times the wall outlet voltage. We get 6,000 volts. This is what we would use for something like a neon sign. They use very high voltages and low currents. This, of course, we'd call a step-up transformer. And on the power grid, the way it's usually set up, we'll have a step-up transformer at the power plant, cranking the voltage up to many, many thousands of volts before we send relatively low currents through the transmission system. Then at the substation, which you've probably seen around town, they're always behind fences and it's a lot of electrical equipment. The voltage gets stepped down, which means the current goes up, for distribution through the neighborhoods. And then again, there's smaller transformers that knock it down to 240 VRMS for your house. That's what comes out of your dryer outlet or your stove. Now, we've said before, large transformers are very efficient, typically 99% or better, so we're going to treat them as perfect just to make things a little bit easier here. If they're perfect, then by energy conservation, we know that whatever energy goes in the primary comes out the secondary. So same for the power, that's just energy per time. Voltage at the primary times current at the primary will equal voltage at the secondary times current at the secondary. Really, there'd be the factor of like 0.99 over here on the left if we're dealing with a real transformer instead of a really perfect one, but close enough. So we can rewrite this. We know the connection between voltages in the primary and secondary. When we rewrite this and figure out the connection between currents, we'll see that it goes in the opposite direction. So if the voltage gets stepped up by a factor of 10, the current is going to get stepped down by a factor of 10. Now, just like the current in one coil can affect the current in another coil, the current in a coil affects the coil itself. This is called self-inductance, so we use capital L for that. And we're going to use this a lot more than mutual inductance in this course. We still measured in henries, and in this case, the flux in the circuit is proportional to the current it carries and the self-inductance. So if we have many turns of wire making up this inductor, this is the flux through them, that product is equal to the inductance times the current. Now, just like we had V equals IR to describe how resistors act in a circuit, or Q equals CV to describe how capacitors act, for inductors we get this, where, again, remember this is a voltage, this EMF, is negative L delta I delta T. This inductance tries to oppose whatever the change in the current would be. So we can see this picture from the other book, the way if we were doing Kirchhoff's laws with the inductor in the circuit, what we would see. If the current's increasing, there's going to effectively be a battery produced here that fights it and tries to push it the other way. If the current's decreasing, the battery points the other way and tries to keep it going like it was. So what's happening here, the EMF is trying to reverse whatever change is happening. And that means the induction is like inertia or mass. Mass doesn't care about velocity, which direction you're going, but it does resist changes in velocity. So just like we found the equations that describe the behavior of resistors and capacitors, and then we found the equations we would need to build one of those things, we can do that for inductors too. We already have the value of B field for a solenoid. It's just mu naught times number of turns per meter times current. The flux we know is B times A, so we could write it like this. We can then use N phi equals Li to say, well, okay, the inductance of the solenoid must be N phi divided by I. And then we can plug in what phi is and say, okay, let's write it as mu naught N squared area of the cylinder that makes up the solenoid divided by the length. And we can keep moving through here and say, well, we could multiply by length over length, since that's just 1. And now we've got the ability to change this capital N squared, number of turns, into number of turns per length. We've got an L left over. We multiply that by the A, and we get the volume. So the inductance is mu naught square of the number of turns per meter times the volume. If we put something inside the solenoid besides air, like iron, where it has a permeability much, much greater than free space, we'd get a much larger value of the inductance. And if you ever made an electromagnet as a kid by winding some wire around a nail and connecting the ends to a battery, you get a much stronger electromagnet with the nail than you get from just the wire itself. Now, if you wonder, what does the solenoid do? Why do we care about it so much? Here's kind of a basic idea. On TV or in movies, if you see people hot wire a car, they're always playing around with wires under the steering wheel, and they're very skinny. Even if we don't know anything about the electrical system of the car, though, we can say that the circuit that connects the key and the battery and the starter can't just be a simple series loop, because we know the wire connecting the battery to the starter is huge, very thick, compared to these skinny little wires on the key side. So what we can do, the solenoid uses a very small current, maybe a few amps, to control the many hundreds of amps of current for the starter. So here's an example, and this probably does not match any car that's made on the road or maybe has ever been made, but this is the idea. We have a solenoid, so we've got thin wires wrapped around this and an iron core, and we've got a spring pulling on this brown block of copper and connected to this piece of iron. If we, right now the brown circuit wire here, the thick one from the battery, that circuit's broken because it's missing this piece. If we run a small current through these thin wires, the solenoid becomes an electromagnet and sucks that iron into the solenoid. That closes this circuit, and now we'll have a solid, thick wire connecting the battery to the starter. This works as a way to let a little current control a big current, and this is also known as a relay. When we turn off we let go of the key switch and we stop running current through the solenoid, then the spring can pull this back. The starter has already started the engine, and we need to disengage it so we don't break it. If you have smart plugs anywhere in your house, where you can turn on with the remote control, you might notice when you do that to, say, turn on a lamp, you hear a little click. That's because there's a relay inside that's going through this same process. The energy that an inductor has usually is compared to kinetic energy because we have to have something moving. We have to have a current. We can use the P equals IV that we've spent so much time with, and energy is power times time, to find that the energy for the inductor is 1/2 Li squared, just like we found the energy for capacitors being like a potential energy, 1/2 CV squared. What do we do with this? Well, we can find the energy density. We use a lowercase u for that, by dividing by the volume. So let's make this a solenoid. Our energy is 1/2 Li squared. Our volume is A times L. We already know the formula for L for a solenoid. We plug it in, and we can end up with this, 1/2 mu naught n squared I squared. If we want to make this even more compact, we can use the fact that we know what the B field is for a solenoid, and we can say that's almost what we've got here. We just have B squared over 2 mu naught. Now, this energy density is even less impressive than what we saw for capacitors, and we saw they were much smaller than batteries, and batteries are generally smaller than gasoline. So a 1 Tesla field would give us a density of about 400,000 joules per cubic meter, which may seem like a lot, but for a capacitor it would be, close to 1,000 times that much, and even bigger than that for lithium-ion batteries. So I don't think anybody's going to be making an inductor-powered electric car anytime soon.